Are there infinitely many primes? This is a proof by contradiction named after the Greek mathematician Euclid. We will assume the opposite and force a contradiction. To start with, what even is a prime number? A prime is a whole number greater than 1 whose only positive divisors are 1 and itself. Numbers like 2, 3, 5, 7, 11, and 13 are prime. However, there also exist composite numbers like 6 that are not prime, as they can be expressed as a product of numbers that are neither 1 nor themselves. A key fact is that every whole number greater than 1 is either prime or can be broken into prime factors. Assume there are only finitely many prime numbers. This is the exact opposite of what we want to prove. Let's denote these numbers p1, p2, p3, and all the way up till pn. Supposedly, this is the complete list of every prime. Now build a new number from the whole list. Multiply all the listed primes together, then add 1. Our new number n is equal to the product of all the primes plus 1. p1 times p2 times all the way till pn represents the product. If the list was 2, 3, and 5, for example, n would equal 2 times 3 times 5 plus 1 equals 31. No listed prime divides n exactly. We can see this as there is a plus 1 at the end of n. In plain English, division by any number in the set pi leaves remainder 1, not 0. But n still has a prime factor. This is due to the key fact we discussed earlier. Since n is bigger than 1, it must be prime itself or have at least one prime divisor. This leads to two cases. Case 1 being that n is prime, and case 2 being that n is divisible by a prime q. Either way, there is a prime connected to n. And we know that q does not belong to the set earlier because q divides n exactly, while every pi in the set earlier leaves a remainder 1. This is a contradiction. The finite list assumption we had earlier fails. We assumed the list of primes was complete. We build n equals the product of all listed primes plus 1. No listed prime divides n, but n has a prime factor still, so the list was not indeed complete. Therefore, there are infinitely many primes.